All right, welcome to the last day of the Maple Conference 2021 and to one of the 3 sessions on Maple in Mathematics today. My name is Jürgen Gerhardt. I'm the session moderator for this session. If you have any questions, you're free to ask those in the Q&A by pressing the Q&A button on your Zoom window. And I will read out the questions after each presentation. And if we have time left at the very end, then there may also be additional time for asking questions. Okay, our first speaker is Yagub Aliyev. Please go ahead, Yagub.
Thank you for giving me this chance. I am from Baku, Azerbaijan, ADA University. I will talk about the best constant inequalities and their applications. I'm considering studying this inequality. On the left side of this inequality, you see the sum of the reciprocals of positive numbers. On the right side, an expression involving a parameter lambda and the product of those positive numbers. Here, I assume that the sum of the numbers is 1 and n is greater than or equal to 2. I put this question in the problem corner of research group in mathematical inequalities and applications back in 2009. And it is still there, unsolved problem. So I was working on this problem for more than 10 years. Unfortunately, alone. I hope that the conference will change this. So if you will look at the left side of this inequality, we will observe that it is increasing as lambda increases. So if we find a certain lambda for which this inequality is true, then it is true also for all smaller lambda. So it is logical to find the maximum possible lambda. If we will study case by case this inequality, then we will notice that for n equals 2, there is no best constant. You can increase lambda indefinitely. For n equals 3, there is a best constant, and it is a very nice number, 25. Lambda equals 25 is the best constant. I published this in American Mathematical Monthly in 2006. This case, n equals 3, has some interesting geometric applications. So you can interpret it as a generalization of Euler's inequality. You know Euler's inequality in triangle geometry, the ratio of circumradius with its inner radius is always greater than or equal to 2. You know this inequality, very famous inequality. Some call it Euler-Chapman inequality. So the inequality that I have shown you for n equals 3 is equivalent to this inequality. As you can see, it is a very sharp refinement of Euler's inequality. R over R is not just greater than or equal to 2, it is greater than or equal to 2 plus 8 times a positive number. Surprisingly, this inequality is true, not just for equilateral triangle, as we usually have for such inequalities, but also for triangle 3, 3, 2, with sides 3, 3, 2. And this triangle 3, 3, 2 is not so remarkable, but for this inequality, it is corresponds to equality keys. This inequality has also some other geometric meanings. For example, this is an inequality involving sides of a triangle. Another inequality about areas. So if I will draw such parallel lines, I gave the details in my video. If I will denote all the areas like in this picture, then this inequality holds true. Another geometric application of this inequality. So these special cases show that it is interesting to study this inequality. The case n equals 4 was studied back in 2007, and I found that the best constant is 30.4, this number. I used Maple to find this. Although it is possible to do this without any computers, but I checked the results using Maple to be sure about this result. It was published in Journal of Inequalities in Pure and Applied Mathematics. For the greater cases, larger cases, n equals 5, n equals 6, etc. I used a new method. I applied multivariable optimization for this problem. And using this method, I proved that for all n, large n, this double inequality is true. So the best constant, there is an upper bound for it. It is n cubed over n minus 2. And there is a lower bound, n squared. So the best constant is something between these two. And for numbers n equals 3, n equals 4, if we will check, we will see that these are really good bounds. So the best constant for n equals 3 is 25. N cubed over n minus 2 gives 27. For n equals 4, the best constant is 30.4. N cubed over n minus 2 gives 32. So this is really good bound, and it gets better and better as you increase n. Now I can also say something about case n equals 5. I couldn't do this before. I can do only now. And for the case n equals 5, the best constant is this large number. I cannot imagine doing this type of research without Maple. So I cannot imagine someone doing this research in 18th century, in 19th century. So without Maple, this is impossible to do. So this is the best constant. And when I evaluate it, approximately it is 40.09. And there are, of course, other cases, n equals 6, but I don't expect to have such nice numbers for those cases. I have, for larger cases, I have approximate formula, which I couldn't prove yet. Anyone interested are invited to work on this problem. We can also work together. So I think the best constant is approximately equal to n plus 1 squared, or n going to infinity. I have also better approximations, n squared plus 15 over 8n. These are just hypotheses. I cannot prove them. There is also problem 2, which I cannot prove again, but if we will prove it, then the problem 1 will be hopefully solved completely. I have to note that this inequality that I studied is not an isolated problem. There are similar inequalities in the literature. So this one is from Mitev's paper in, again, Journal of Inequalities in Pure and Applied Mathematics from 2003. And as you can see, there is a similarity between this inequality and our inequality. In our inequality, sum of 1 over xi was greater than or equal to something. This is less than or equal. So the best constant for this inequality is known. It is n squared minus n to the n divided by n minus 1 over n minus 1. Mitev proved this for all n. Okay. So the problem for this inequality is completely solved. This inequality also has some geometric meanings that I mentioned here. That's all. Thank you for giving me this opportunity, this chance. I am ready to answer your questions if you have any.
Thank you very much, Yagub. The floor is open for questions. I have one question. So the optimal value for lambda seems to always be an algebraic number. Do you have any bounds on the degree for larger values of n?
Actually, yes, we can prove that the order of the algebraic number will be of order n minus 2. N minus 2. I think this can be proved, but I didn't work on this seriously. Yes, you are right. If n equals 5, for example, we have cubic root here.
No, that's not cubic. I mean, that's if you take, it's a cube root of a square root, so the total degree there is 6.
So total degree is okay. So the largest root that I expect there can be n minus 2, but there can be nested radicals. You are right.
So that sounds more like it's n factorial or n minus 1 factorial.
It is possible, yes. Good point. Thank you for telling me this. I never thought about this.
Okay, and one other question. So your applications for the case n equals 3 are very nice. Your geometric applications. Are you aware of any applications, say, for n equals 4 or higher values, larger values of n?
I have not found any applications for other cases. Actually, I came to this inequality from geometry. So I was studying these geometric problems, and then I distilled it to algebraic form. And then I thought maybe I can generalize it for higher dimensions and for case n equals 2. And then I saw that this is a really interesting inequality. So I have only applications for n equals 3, and this is the origin of the problem. That's where I came to this problem.
Okay. Thank you very much. And we'll move on to the next speaker. So the next speaker is Zhenbing Zeng. Can you share your screen, please? Okay. Please go ahead. And you're muted. You have to unmute yourself so we can hear you.
Oh, good. So I'm trying to do the full screen because no. Oh, good. So here, B. So the title of my talk is machine proof for an inequality for the sum of distances between 4 points on the unit hemisphere using Maple software. So this is a joint work with my student Xuyao Chen, Lu Jian, and Chen Liangyu. And so this is the inequality. So suppose we have 4 points on the upper unit hemisphere. We want to find the largest value of the sum of the mutual Euclidean distance. Here is the definition of the Euclidean distance. And we guess the result by symmetry. One possible result is we put 3 points on the equator to form an regular triangle, and the 4th point on the North Pole. And another possibility is we put 4 points on the equator so that the 4 points form an regular square. Actually, in the beginning, we guessed the first configuration, but after some numerical computation, we found the second one was better than the first one. And here we do some Monte Carlo test, and we also did some global grid search, which we divide the cube into a lot of small cubes with edge of 1/64. Then we drop those small cubes that has no intersections with the hemisphere, and we test all possible allocations of 4 points, and which this shows that the 4 plus 4 multiplied square root of 2 would be the largest sum. And so this is the result formulated by the numerical computation. So for any 4 points on the hemisphere of unit radius, the sum of their distances is not larger than this number, 4 plus 4 times square root of 2. And up to a congruent transformation, the optimal configuration is formed by 4 points on the equator, which form a regular square. So when we analyze this inequality by without machine, we proved a lemma like this. If 4 points form an optimal configuration, then the convex hull of these 4 points must contain the center O of the hemisphere. Using this lemma, we can prove that in the optimal configuration, at least 3 points are located on the equator. So without loss of generality, we may fix 1 point A at a special point. So what is difficult if we use the Lagrange multiplier method? The problem was computational complexity. So we were not able to find the proof by hand computation. So we try use Maple for doing this problem. So the approach contains 2 parts. In the first part, we do symbolic computation using Maple. We construct 3 neighborhoods UVW around the 3 points B, C, D, so that whenever B, C, D are located in UVW in these 3 neighborhoods, the inequality is valid. So where UVW is some box-like neighborhood. And in the second part, we do the numeric computation, mainly numeric computation, but exact numeric computation with Maple. So with other software like Python, this part is not easy to do. So Maple also plays very important role in this part. So we reduce the computation to a new problem, which we fix point on the equator, and we
It appears that our presenter may have lost connection.
Yeah, when something like that happens, it's always the question, is it me or is it the other person?
Yeah, no, I think in this case it's on the presenter side of things. Maybe we'll just give him a couple minutes to see if it can come back, or
So that's funny. He can move his slides, but we don't see his video or don't hear him.
So
Yes, he seems to be coming in sort of in and out and
Yeah.
in little 1 second bursts.
Yeah. Zhenbing, can you try turning off your video? I think you have a limited bandwidth. We can't even hear you right now. And now you're muted, so you have to unmute yourself. We cannot hear what you're saying because you're on mute, Zhenbing. No, unfortunately, we still cannot hear. I'm not sure what happened to
he's
the audio.
unmuted, but
Yeah.
okay. Well,
Anyway, the time is up. So I'm not sure how we want to do this with the questions if we can't hear you. Zhenbing, are you able to type the answers to the questions in the chat? Let's see whether that works. So that's a very nice result. One question that I have is, I'm curious if you try a purely numerical optimization package in Maple or otherwise, which answer do you get? Do you get the right answer or do you get something else? And again, we cannot hear you, so you have to type your answer in the chat. And or maybe you can type it on the screen. We can see your screen for some reason. If you open an editor and type the answer there, we can also read it.
oh, he seems to have typed something in the chat.
Okay.
We can see you, but we can't hear you.
We cannot hear you, so can you type your answer to the question in the chat? So the question was, if you use a purely numerical method, does it give you the right answer for this problem? Yeah, so he seems to be answering a different question. The other question was why the limit, I had that same question too, by the way, why the limitation to the hemisphere, not the full sphere? And the answer is that for the case of 4 points, the answer for the full sphere is known and it is easy. It's just a regular tetrahedron, I think. But for 5 points, the answer is more difficult in the case of the full sphere.
yes.
Okay, thank you. So unfortunately, we have to move on. So maybe if there are additional questions, we can try and ask and get them answered at the end of the session, if there's time left. So thank you very much again to the speaker. And our next speaker would be Erica Wang, but she doesn't seem to be here. So we move on to the last speaker right away. So that's Aishat Olagunju and David Jeffrey. And David Jeffrey will start. Please, David.
There we are. So you can see the screen?
Yes, we can.
Okay, thank you very much for allowing me to make this presentation at the conference. Aishat Olagunju is my graduate student, and of course, in the usual tradition, did all the work, and I'm doing the presentation. Pythagorean triples, quadruples, and beyond. It's not quite, I think, what we call it. Anyway, oh, pardon me, I've jumped too far. So what drove this talk? So our main interest is actually in Pythagorean vectors. A vector is a vector of integers with an integer 2 norm, which means it's all the elements of a Pythagorean n-triple, except for the end element. So obviously we first n-1 elements go into the vector, and then the nth one is the norm. One difference is that a Pythagorean vector can have 0 or negative elements, whereas traditionally an n-tuple does not have zeros and is all positive integers. So when we started to work on this, we were impressed that after 4,000 years, people are still actively devising and publishing ways to generate Pythagorean triples, and to a lesser extent quadruples and quintuples. And so I set Aishat to collect a historical collection of references and implement many of them in Maple. And so the first part of this talk is going to be a historical comment on that. There are a few observations which I think are new towards the end, but mostly it's just an interesting piece of history. We start with Euclid. So there are older documents, such as the clay tablet called Plimpton 422, which is dated at about 4,000 years old, is Babylonian, but it's interpreted as containing a list of triples, but doesn't document how you generate them. So the first evidence that we could find was the famous entry in Euclid's Elements on Pythagorean triples. So that's our starting point. That's more than 2,000 years old. Then we found a book by a well-known rabbit breeder, Leonardo of Pisa, who, in addition to the book that made him famous, which introduced Hindu-Arabic numerals into Europe, also wrote a book called The Square of Squares, in which he generated Pythagorean triples. As a result of this, I discovered for the first time that Leonardo of Pisa was not renamed Fibonacci until the 19th century by a historian of mathematics. And he was not known by the name Fibonacci in his own lifetime. We've got that one implemented in Maple. We could show you that. His method does not find all triples, but we include him just because he's famous. Another famous name that we found was Euler. All of Euler's papers are available on the internet. However, a large number of them, including the one that we found, is only in Latin. So I faked a translation with my schoolboy Latin, and the equations can be interpreted anyway. He also distracted us by not only talking about triples, but also quadruples. He also created magic squares and similar things. And it was also interesting that he preferred trig functions for investigating these tuples rather than polynomials. And we have Maple worksheets showing some of his work as well. And then just to prove my statement that this is going on for 2,000 years at least, our final examples come from this century, in fact, this very year, because in Maple Primes, one of the users has posted a method of calculating triples using ternary trees, which is a data structure in which each node has at most 3 child nodes. And he does this by a method of taking a Pythagorean triple and then multiplying it by a set of 3 matrices and generating 3 new triples from the given one. This was all implemented by Aishat, and she could, if you're interested, tell you a bit more about what she's done. And we have, these are the matrices that have been used. One set was generated by a fellow named Berggren, and another by someone named Price. And you see down here at the bottom of the screen, I start with a triple, multiply by any one of the 3 Berggren matrices, and I get 3 new triples. And there is the ternary tree. Aishat produced this using Tixie, which I must say is very good. I've never learned Tixie myself. Anyway, a nice little picture of that. And this is similar to the one that was posted on Maple Primes. I'll skip over that one. We can come back to it. It's a bit crazy one. One of the other things that people like to do is to turn triples into pictures. So what they actually do is turn them into 2-dimensional Pythagorean vectors and then plot the vectors as points. And the point that I'm making here is the picture you get out depends upon how you order your triples, or Pythagorean vectors, as it happens. For example, some people order their triples by taking Euclid's algorithm, and which always starts with an odd number and then goes to an even number. And then that is the ordering they use to give the triples. Whereas other people are careful always to make the smallest element the first element, then so they have an ascending list. And you get 2 different pictures depending upon how you do it. That's the picture you get if you accept the Euclidean ordering, i.e. always starting with an odd element and then going to an even element. And people love to look at these obvious lines that are going through the picture. And you can make explanations of where these lineups of lines come from. By the way, these are only Pythagorean primitive triples, i.e. there is no GCD, common GCD other than 1. If you include all Pythagorean triples, you get a much denser picture, of course, and people have put those denser pictures on the internet as well. If we choose the other popular ordering, which is to have them in ascending order, you get this, because of course everything's got to be cramped up into the top sort of triangular shape there. This shape also has its own interesting lines, as you can see, and we can look at how to describe those as well. I don't think we've written that up yet, but we're still working on it. Going on to quadruples, so our main interest is actually not in triples, but in higher dimensions. There is a parametric generation for quadruples. So there's a pair of authors in Austria, Frisch and Wasserstein, who have made generating n-tuples of higher order by polynomials a research topic of theirs. And they've gone quadruples, quintuples, sextuples, I think even some septuples, but by that stage, the Pythagorean parameterization becomes extremely unwieldy, and that's where they've stopped up till now. A slightly more fun way to generate quadruples or higher order terms is to chain together triples. So you start with 5, 12, 13, then you find a second triple that starts with 13, and then you put the 2 of them together and you get 5, 12, 84, 85. And Aishat has written a Maple program that continues to do that and makes triples, makes Pythagorean vectors of much longer length by chaining triples together, which is rather fun. Here's a little bit on, we've also put Euler's results into a Maple worksheet. He used 8 parameters and produced this 4x4 matrix. He didn't call them matrices, of course, he just presented them as a table, but we today would call them matrices. And if you square each element of, so this is not a magic square. You see that he repeats numbers, which is sort of not fair for magic squares. And of course, they have signs as well. But if you square each element of this matrix, which is easy to do in Maple, you end up with a magic square. So rows, columns, and diagonals all add to 1690. So these are squares of squares, magic squares of squares, or squares of magic squares. I'm not certain how you would say it. And Euler was doing that as part of his speculations. He also, it's not obvious from this, but these columns are actually orthogonal to each other. Although he didn't say why he wanted that to be the case, but it is. And then we can go on to higher dimensions. For example, an arbitrary n-tuple can be made by the chaining method. So 1, 2, 2, 3 is a primitive Pythagorean quadruple. So if I take 1, 2, 2, and then the next element would be 3. So I multiply 1, 2, 2 by all of this, and I keep going. I can make a chain that goes to length n. And then the final thing, which I think is new, I don't think people have done this, is what we did is we said, okay, let's take all vectors of length less than 20. How many n-tuples are there in each dimension less than 20? And it's interesting, I think, that so in 3 dimensions, there are only 3 triples whose last element is less than 20. That's 3, 4, 5, 5, 12, 13, and another one ending in 17. But as you go to higher dimensions, it becomes a lot easier to find tuples. So here we get them up. You see the number of n tuples for each dimension increases all the way up until dimension 8. Then you're starting to run into the trouble that clearly with eventually you're going to get, certainly by dimension 20, the smallest vector you can have is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, which is 20, and that's not an n-tuple. So by the time you get to 20, you must go back to 0. So there must be a maximum dimension where the number of n-tuples less than 20 is a maximum, and that happens to be dimension 8. So I think that's a new observation. That's it. So if you've got, so I've got here references. Here is Fibonacci translated by Ziegler, and you can get that in English at 1987, The Book of Squares. Euler's archive is on this internet website, and the paper we chose was paper 407. So those of you who are musicians will know about Köchel numbers for Mozart. So for Euler, there are Enstrom numbers, and this is Enstrom number 407. This is 2018, is this Bergson trees, and down here on the next page, somewhere, yes, here is a reference to Maple Prime's post February 2021, and there are some other miscellaneous sources as well. And Frisch and Wasserstein, as I said, have made quite a theme of their research, polynomial parameterizations of Pythagorean n-tuples. So with that, I'll see if there are any questions, and maybe Aishat can put on her video and answer one for you.
Actually, yeah, we're way over time, David. But, so let's wait for questions from the audience first. So there's some some postings with references in the chat. And I'll have a question. So I'm assuming Frisch and Wasserstein's parametrization gets all such Pythagorean triplets, or at least all the primitive ones. Do you get repetitions?
Yes, you do. So they one of the things that Frisch and Wasserstein did was they said, well, if you use Euclid's parameterization, you always start off with an odd number and then go to an even number. So if you want all of the triples that start with an even number and then go to an odd number, even though, of course, it's the same triple in a sense, you need a second parameterization, which is also the Euclid parameterization, but you just change the order. So you go to m squared minus n squared, as opposed to the other one. So they said, so really that's two parameterizations. So the slide I skipped over is an attempt with 4 parameters to make a single parameterization that generates all triples, even if they are equivalent in the sense that 3, 4, 5 is the same as 4, 3, 5. But they get all of those plus others. And of course, you get non-primitive ones as well.
Right. So what I meant actually is I understand that you get permutations, and that's why you get multiples. But do you even get exactly the same in the same ordering more than once?
I don't think so. I've not actually looked at that, but I've not thought to try and, yeah, I'll admit, we haven't looked at that. We'll let you know.
There's another question that just came in the chat. Can you follow the analysis of Wildberger and Mansfield that the list of triples in Plimpton is a trigonometric table?
I don't know that reference. Is that Liz Mansfield that we're talking about? Anyway, I'll have to look at that reference. But yes, one of the interesting, if the trig tables, in the submitted paper to the conference, we have a geometrical figure of a triangle. It's two triangles inscribed inside a circle, and we show that the tangent of one angle gives you the equivalent to the Euclidean polynomial parameterization, if that's what the basis of the question is. And Euler has in his paper, has quite a lot of work on using trig functions, but my Latin sort of broke down as I tried to figure out exactly what he was doing. But we could also make the comparison there.
Okay, thank you. Are there any more questions for the other presenters of the session? That doesn't seem to be the case. So we have about 3 minutes left. So if Aishat wants to show the video in those 3 minutes, please go ahead.
Aishat, have you got, I can put up the page of the Bergson matrices, and you can say what you did if you like, or I could put up your Maple worksheet. Why don't I?
2.5 minutes.
Oh, well, doesn't matter.
Hi. I can share the screen.
Okay, I'll stop sharing.
Okay, then I can share the screen for the triples then. Is it visible?
Yep, we can see your screen.
Okay, thank you. What I did here was to take each Bergman matrix and perform matrix multiplication with each one. Using 3, 4, 5 as an example, if you perform matrix multiplication with B1, which is the first Bergman matrix, you get 15, 8, 17. And you perform the same matrix multiplication with the B2 and the B3, you have this. Going to the next slide, you have this tree. And if you follow each node, which is like a tree with 3 branches, you get 3 new triples. And each one also produces 3 new triples, and it goes on and on and on like that. Same way with the prize matrices, you have brand new matrices, brand new triples, and it goes on and on until infinity. Yeah, that's it.
Okay,
Yes.
thank you very much. And if there are no other questions, then I'd like to thank all the speakers of this session again. There's going to be a 15-minute break now before the start of the next session and the last session for today. Thank you very much, everybody.